Hi Pre-Calc. In this lesson, we are taking care of graphs of secant, cosecant, tangent, and cotangent. So we've already done sine and cosine, and now we're moving on to the other four of the six. So not only are we going to graph these new functions, but we're also going to continue identifying amplitudes, periods, phase shifts, vertical shifts, etc. I guess just that of those four new ones. So we're going to start out with cosecant. So just a reminder, cosecant is the reciprocal of your sine function. Okay. So another way to write that is cosecant of x is equal to 1 over sine of x. Although I don't think that's as helpful as just remembering that if you have a fraction, you're just going to flip-flop the numerator and denominator. Okay, so what we have in this table, this very lengthy table, is we have degrees on top. Those are going to represent our x values on the graph. And then we have our sine function. So those are going to be the y values on the graph that we're going to create, except we're not actually going to create that one. We're going to create the reciprocal of that, but it's there so that we can easily do that. And then for our last row here, our cosecant of x, that's going to be the y value on the graph we're creating. So, so here's our x-axis, and here's our y-axis on our graph. Okay. So what I'm going to do to start off here is most of our sine values are already in fraction form, but for the ones that aren't, I'm just going to really quickly make them into fractions just by putting them all over 1. Okay. And then what we're going to do is we're just going to flip-flop them to get our cosecant value. So 0 over 1 becomes 1 over 0. And that's a problem. You can't divide by 0 in math. So that one ends up being undefined. Or you could just put a slash there or whatever, but we can't do that one. 1 over 2 becomes 2 over 1, or just 2. Square root of 2 over 2 becomes 2 over the square root of 2. So flip-flop those. And I just grabbed a Desmos calculator and typed that in. And we're just going to round to the nearest tenth. We don't need to be perfect here, so I'm just going to go with 1.4. And then square root of 3 over 2, we flip-flop it. So I typed in 2 divided by the square root of 3. And we get 1.15, so I'll just round that up to 1.2. 1 over 1 becomes 1 over 1. That's easy enough. And then we're just going to start repeating a bunch of this stuff. So square root of 3 over 2 we've already done. That's 1.2. Square root of 2 over 2, we flip-flop that. We get 1.4. 2. 0 divided by 1 becomes 1 over 0. That's undefined. Then we're going to have negative 2 and negative 1.4 and negative 1.2. 1 divided by negative 1 is negative 1. Negative 1.2. And negative 1.4, negative 2, and then again 1 divided by 0, which is undefined. All right. At that point, we are going to start graphing this stuff. So I'm going to go 0 degrees. I'm going to put 180 degrees somewhere in the middle. Put 360 degrees. Somewhere near the end. I'll cut that in half. Got 90 there. Cut this in half. 270. And then we're going to have 315. And 225. And just get these as neat as possible. There's our 135. And our 45. Okay, so I actually didn't put every single one on there. I didn't do the 30s and the 60s and all that. I kind of just went and did the 45s. And that's going to be fine to get a picture of what the parent function looks like. I think that'll be sufficient. And then I think we're going to need 1, and then we go up to 2. So we should probably get a 2 on there. I don't think we go any higher than that. And then we should go to negative 1 and negative 2. So what happens when we start graphing this? So at 0, when our x is 0 right here, or to see that now. We are undefined. So actually what happens there is we have an asymptote. We have a vertical asymptote there. I'm going to go and do the rest of those. We have another vertical asymptote at 180 degrees. Scroll that up a little bit. At 180 degrees. And then we have another vertical asymptote at 360 degrees. All right, and then I'm just going to go kind of skip around here. At 90 degrees, I'm at 1. That's kind of a nice one. At 45 degrees, I'm at 1.4. At 135 degrees, I'm at 1.4. So you can kind of see what's happening here. We kind of end up making these parabola-looking things. Like that. Make those as neat as possible. Then I'm going to go to 270 degrees, which is -1. So somewhere down here. And then let's see, at 225 degrees, we are at -1.4. Somewhere in here. 315, we are symmetrical. And we end up looking like that. So, and then we keep repeating. So we would end up kind of with the same thing over here. If we kept going into negative land, we would have an upside down one then. Over there. That's not the best because we kind of ran out of space there. But I just kind of wanted to give you an idea of what the parent function of cosecant looks like. Now, we can do a pretty good job making a sketch. It's not the easiest to do on a smartboard, so I would do it a little better if I were on paper, and I would take my time probably a little bit more, but I didn't want to bore you guys to death. But what you can do to get an even better picture of this is if you go on Desmos and you, first of all, hit your gear, or the wrench, I guess it's a wrench. We're in degrees in this case, so you want to change it to degrees. And then just kind of think about what you want for an x-axis. It's fine if we start at -10. Maybe let's go a little bit beyond 360. Maybe let's go to like 400. And then we can keep our steps. It doesn't really matter. You can kind of just leave that one. And then for your y-axis, let's go like -3 to 3. And then get out of that, and then let's type in cosecant of x. And I'm actually going to zoom out a little more, and then hide the keyboard so we can see it. So there we go. That's pretty much what we ended up with. Now the interesting thing, I think, is if we type in our sine of x. That kind of helps us put everything together. So what happens, the big thing with this lesson is kind of realizing where your asymptotes are. Your asymptotes are going to happen where your original graph, where your sine function went through the x-axis. Now, that's the case if there's not a vertical shift. If there's a vertical shift, they actually happen where your graph crosses the midline. Okay, so if we went up or down, we got to kind of adjust our asymptotes a little bit. But on a standard parent function graph or one without a vertical shift, your asymptotes happen at those zeros. The other cool thing is kind of the bottom of your parabolas. They happen at the peaks and valleys of your original function. So when you sketch these by hand, instead of making that whole nasty long looking table, all you're going to do is you're going to start with either the sine or cosine function, depending on if it is a cosecant or secant, and then you're going to use those two things that I just talked about. The fact that the asymptotes happen where the graph touches the midline, and then the fact that the secants or cosecants kind of start at the peaks and valleys of the sine of the cosine function. Okay, so I think it's always nice to look at Desmos and kind of see what it comes up with and to pick out some patterns and things from there. All right, moving on to secant. I actually don't think I'm going to do this whole entire table, but it's the same idea. Secant is the reciprocal of cosine. So if we were going to go through and do this whole entire parent function, we would, again, probably make these guys into fractions, and then we would flip-flop them all. So 1, and then we would have 2 divided by the square root of 3, which is our, ends up being about 1.2 and about 1.4, and then 2, and then we end up being undefined right here. So we are going to end up having asymptotes again, but they're going to be in different locations. This time your asymptotes are going to be at 90 degrees and 270 degrees, so a little bit different there. So I am not going to do that whole entire table. I will sketch kind of a rough picture of what the what this parent graph ends up looking like, and then you can either copy it down or print it or do what you need to do. But you are going to end up with asymptotes at 0 degree, sorry, not 0 degrees, 90 degrees. This would be at negative 90 degrees. You would have another one at 270 degrees. Another one at 450 degrees. I don't think we need to go that far. This is 1. So you're going to end up one of these guys there. You're going to end up -1. Like so, and then you would end up repeating yourself right there. So again, I think that's it's nice to make the table and see where all of this is coming from, seeing that these things don't just kind of appear out of nowhere. Anytime you want to make a graph, you can always create a table, but it's always going to look a little bit better if you do it on an actual graphing software. So in this case, this is our secant, which is the reciprocal of cosine. And then you can kind of see it's basically exactly what we just did with cosecant and sine, except for, yeah, we're using the cosine parent function instead. So asymptotes are happening at these zeros, so 270, 90, -90, and then your upward and downward rainbows are happening at those different locations. So always a good idea to type your stuff in and kind of play around with it and make sure that what you have on your paper is looking the way that it's supposed to be looking. All right, so going into some directions on what you're going to be doing when you're doing these by hand. If you were graphing secant or cosecant, I already talked about this a little bit, lightly sketch in your either sine or cosine curve. So sine is what you're going to do if you're working with cosecant, and cosine is what you're going to draw if you are working with secant. Okay, at that point, you're going to draw in your asymptotes where your sine or cosine curves are zeros, i.e. where your secant or cosecant values are going to be undefined. Okay, if you have a vertical shift, use the midline. Use the points where your sine or cosine curve crosses the midline, not the x-axis, because your whole graph is going to be kind of moved up or down. And then number 3, draw the reciprocal function, which is your secant or your cosecant. All right, moving on to your transformations. This isn't going to be anything very new. Since you already did sine and cosine, it's kind of all the same. So amplitude, period, phase shift, and vertical shift are all coming from the exact same location. So just kind of note to self, these are the same as your sine and cosine. So amplitude, what it does, in this case, they're technically, actually, I guess I shouldn't have said it's exactly the same as sine and cosine because the amplitude is a little bit different. If you look back at our graphs, you can kind of tell that amplitude isn't really a thing because our graphs are kind of either going up forever or down forever. So amplitude is not very easily measured on these guys. So technically there really isn't an amplitude. But when you are sketching your sine or cosine function to get these things started, you are going to need to use amplitude. and you're going to find it by looking for that a value, that number that's out front. All right. Second thing, period. That is exactly the same as what it was before. It kind of has to do with your b value, but you have to do a little bit of work. You are either doing 360 degrees divided by your b, or you are doing 2 pi divided by your b value. So a little extra work, but you're using your b value there. Okay. Your phase shift, same as what you were doing before, where you are setting your parentheses equal to 0 and then solving. And you're going to use your c value. What color did I use there? Purple. And then your vertical shift is your d value. So you're up and down there. Where did I use? Green. Make it a little pretty. All right, so that's the same as what it was before. All right, so let's hop into an example here. So if we were just kind of following through with the steps I went over a couple slides ago, first thing we're going to do is we are going to identify whether it's a secant or a cosecant, and we're going to sketch its reciprocal. So secant is a cosine graph. So we're going to start by sketching basically the same exact thing except replacing secant with cosine. So y equals 1/2 cosine 2x plus 45 degrees. Okay, so before we do that, let's fill in our amplitude, period, phase shift, and vertical shift. So technically for all of these guys, there's no amplitude, but I want to remember what the amplitude of the cosine function is, and it's 1/2. So I'm just going to put parentheses 1/2. If you see that on the answer key, that's what I mean, just kind of keeping in mind what the amplitude of the cosine graph was. Okay, period. To do period, in this case, it looks like we're dealing with degrees. I should put a degree sign there. So we're going to do 360 degrees divided by our b value, which is 2. So our period is 180 degrees. Our phase shift is where we want to set our parentheses equal to 0. So 2x plus 45 equals 0. 2x is negative 45. Divide those in half, and we end up with negative 22.5 for our phase shift, and that's in degrees also. And then vertical shift, we don't have anything on the outside here. We don't have a d, so there is no vertical shift in this case. Okay, so to kind of figure out what this graph looks like, I like to figure out where we're kind of starting and where we're ending a period. So we are going to start right here at negative 22.5 degrees. And then we're going to end, we are going to end 180 degrees later, and it's 180 because that's our period. And that ends up being 157.5 degrees. So, kind of some weird numbers. All right. So at that point, I am just going to kind of get a rough sketch going here. I'm still always going to call this 0. I think going from -1 to +1 is going to be sufficient when we have our amplitude is 1/2. So we're certainly not going to go beyond 1. You can throw some halves in there because that's what we're going to be doing. And let's see, we kind of want to go, I'm going to put maybe 90 degrees here, maybe 180 degrees here. I'm going to cut that in half. That's going to give us 135. Cut this in half. That's going to give us 45. And then let's maybe go back to -90 and -45. And you might choose different numbers than that, but I think that's going to be sufficient for what we need there. Okay. Now we're dealing with the cosine function. So the original cosine function, remember, kind of starts right here. I'm just going to put a little green dot there. There's our original cosine function. Now we're doing a couple things. We are kind of squishing it down in half. So we're no longer going to be at 1, we're going to be down at a half. We're going to be right here. And then we are also sliding back negative 22.5 degrees, which is halfway between 0 and negative 45. So we are going to start right here. And then we are going to go through an entire cycle, and we are going to end up in that exact same spot at 157.5 degrees, which is about right there, okay? So we kind of have to picture what this is going to look like. So we're kind of halfway through, we're going to be about here. And we kind of need to just make this look as good as we can, something like that. Okay, so we need to do that even though we are not graphing technically the cosine function. We're technically doing a secant function, and I think I'll usually probably do that with a dashed line if I'm doing it on paper. But if I have different colors here, I think that's fine. Okay. Now the important things that we need to find here are the zeros. Those become our asymptotes. So we have an asymptote here, and we have another asymptote here, and then we're going to build our secant function right off of that. I'm going to do it in maybe like purple, maybe something totally different. Okay, so we're going to have this, and then we're going to have this, and we're going to have another one. Like that. Okay, and again, you can always hop onto Desmos and double check your work there. It's not going to be perfectly perfect when you're doing it by hand, but it should look nice. It should be close to accurate. But yeah, you can go on Desmos and get a perfect picture of it just to make sure. All right, we are going to do a second example here, and this time we are using cosecant. And we also see a pi, so this one's going to be in radians. That wasn't obvious. We're going to do radians this time instead of degrees. So first thing we want to do is we want to think about what the sketch of 3 sine of x minus pi plus 2 would look like, and kind of go from there. So we're going to sketch that guy. So amplitude. There's no amplitude for the cosecant function, but I do want to remember that the amplitude of the sine function is going to be 3. The period in this case is just a regular old 2 pi. Reason there, our b value is just 1, so 2 pi divided by 1 is just 2 pi. So regular period. Phase shift, x minus pi is equal to 0. Add pi to both sides, and you're going to end up with a phase shift of pi. And then vertical shift, we do have one on this. It is going to be 2. Our number on the outside here is 2. So kind of to just remember what we're doing here, we are going to start one cycle over at pi. So typically your sine function would start at 0, 0. But in this case, we're going to shift it over, and then it's going to end. We're going to take our starting point, and we're going to add 1 period to it, which is 2 pi in this case. So it's going to end at 3 pi. Okay, so when I'm sketching this graph, we don't really need much in negative land here. We have a phase shift that kind of brings us in the positive x direction. So I'm not going to worry about anything over on the negative side of things. But I'm going to do a few pi's here. So I'm going to do pi, and 2 pi, and 3 pi, and then I'm just going to kind of put some tick marks in between. And then in this case, we do have both a vertical shift and an amplitude that's greater than 1. So we are going to end up going a little bit higher in this case. I think the highest we're going to need to go is 5. And you might not know that right off the bat. So that's something you can kind of deal with later. I don't really like how the spacing was there. 1, 2, 3, 4, 5. I like that a little bit better. And then we're not going to go too far down into negative land here. I'll just do 2 of them, but I think we're going to need 5. All right, so kind of just think about where your sine function would typically start. So I'm just going to grab a red marker, and we're kind of going to ignore this stuff later, but just so you guys can see what I'm doing. So typically sine function would start at 0, 0, but we do have a phase shift in this case, so we're shifting it over to technically start over at pi instead of at 0. And then another thing, well, two more things are happening. We have an amplitude of 3. So we're going to want to multiply that y value by 3, which doesn't do anything. 0 times 3, our y value is 0. We're already on the floor. So multiplying by 3 doesn't really do anything, but there is a vertical shift of 2. So we're going to want to slide it up to 2. So that's kind of where we're starting. We're starting over pi and up 2. And then we're going to do a very amplified sine curve from there. So if you think about kind of your normal sine curve, we kind of go up and then back down and then back up again. So we are going to end, we're going to end here at 3 pi, and then we're going to kind of be back in the middle at 2 pi. So we're going to go, up and then down and then back up. But our amplitude is 3. So that is where, since we're kind of starting at 2, we're going up all the way up here to 5, and then down here at -1. So hopefully you can kind of picture what I'm doing there in your head. So it's going to look like that. So it's amplified and scooched over to the right, but it still has your regular period of 2 pi. Okay, now again, typically I'll kind of make those dash lines if I'm just using a pencil, but since I have a couple different markers to choose from, I'll just do it that way. Now, anytime you have a vertical shift, it's probably a good idea to fill in your midline. So your midline happens where that vertical shift is. So there's our midline on the graph. The reason why we need to do that is because that's where our asymptotes come into play on this one. So we have asymptotes that run here, so it's where your graph crosses that midline. So here and here, I really should have gone exactly through 2 pi, I kind of missed. And there, okay, so there are our asymptotes. Now when we go to fill in our actual cosecant function, we're going to go off of this guy in the opposite direction, off of this guy in the opposite direction, staying between those asymptotes, okay? And that's all you need to do. Technically, when you're going through these, you only need to graph one cycle. So that graph isn't super duper exciting. You can always do more than one cycle if you want. I know there were a couple on the answer key when I was doing it that I ended up with more than one cycle, just because I think sometimes it ends up a little better that way. But all you're required to do is one cycle. All right, sorry this video is long. We're already almost at a half an hour and we're still going. We're doing tangent and cotangent next, okay? So tangent, the table is kind of already filled in here for you. So what we did to fill in this table is we grabbed the unit circle and we went around it. And to find tangent, you find your y value and divide it by your x value, y over x. And you go through and you kind of see that some of our same locations pop up here. We do end up with a couple different places where we are undefined. And that's where our asymptotes are going to happen. So I'm going to make just a really rough sketch here of what tangent looks like. Tangent, you kind of just need to remember that it makes this sort of shape. Do the best job drawing that. And it goes through 0, 0. Okay, your basic parent tangent function goes through 0, 0. So your asymptotes are going to happen at 90 degrees and what was the other one? 270 degrees. I'm going to throw a 180 degrees in there and then a 360. So your asymptotes are here. And then there's going to be another one at -90 if we want to throw that one in as well. Okay, and then your graph, switch colors here so it looks a little better. Your graph is going to look like this. It's going to go through 360. 360, 0. You can see that on there. So I'm just kind of grabbing some of the important points here. Like so. So that's what your tangent parent function looks like. Again, the big things there are just kind of the shape of the graph. So it kind of looks like, I kind of compare it to the cubic function, the cubic parent function. It goes through 0, 0, and then those asymptotes are at -90, 90, 270, etc. All right, I'm going to skip that one. I don't think we need to do that. Cotangent. Cotangent, what you need to remember here is that, well, it's the reciprocal of tangent. So we could do the same thing as what we did before. We could go through the table and kind of do the reciprocal of every single one of these. I'm not going to do it for every one, but I'll do it for a couple important points here. So tangent at 0 degrees was 0 over 1. If we flip-flop that, we end up with 1 over 0, which is undefined. So you're going to have an asymptote on cotangent at 0. So one of your asymptotes is right there. Another asymptote would be at 180 degrees. So I'm going to fill that one in. 180, put 90 in here. You're going to have an asymptote there. You're going to have another one at, 360 degrees. I'll put 270 in there as well. Okay, so your asymptotes are a little bit different there. Now, what's happening at 90 degrees? So at 90 degrees, we were undefined. So in the tangent function, we were actually at 1 over 0 there. If we flip-flop that for cotangent, we're at 0 over 1, which is 0. So 90, 0 is a point. Same at 270. 270 was 1 over 0 for tangent. It's now 0 over 1 for cotangent, which is 0. So we're here, okay? Now cotangent goes kind of in the opposite direction. So cotangent looks like this. So if we are sketching the parent function here, we want to stay between the asymptotes. Something like that. That wasn't the best. That one was a little better. Like so. So yeah, those don't look great. And then again, you can always hop on Desmos anytime you are wondering exactly what something looks like. We can do tangent and we can do cotangent, and you get a really pretty really pretty picture there. So you can see that tangent is in black, so that one kind of goes upwards, and then cotangent is in red, that one goes downwards. You can see where these zeros are. You can kind of play around with that to get a better idea of what that should look like. Skip that one. All right, and then for the different transformations here, there are some different things that go on with tangent and cotangent here, so let's just be careful when we talk about these. The parent function or the transformation functions look very similar. Amplitude, there is really no amplitude, but there is a vertical stretch. So where we would kind of normally think about amplitude, think about vertical stretch instead. And you're going to find that at your A value. Same places where you normally find it. Now, this is important. The period here is different than it was with all of our other ones, with sine, cosine, secant, cosecant. It is no longer 360 degrees. It is 180 degrees. Okay? So it is the length of your cycle, but it is 180 over b, or pi over b. Okay, so take note of that. If we flip back here to one of our pictures, you can see that a cycle here kind of starts at 0, ends at 180, and then you repeat from there. So 180 degrees instead of 360 degrees. So you're going to find that, again, at your B value. Phase shift, same thing. Set your parentheses equal to 0 and solve. That's nothing new. You're going to find that at your C value. And then your vertical shift is at your D value. That's your up-down. And then in this one, you are going to run into a couple negative ones. So regular tangent without a negative is going to look like this. And regular cotangent is going to look like this. But if you have a negative tangent, it's going to kind of do the opposite. And if you have a negative cotangent, it's going to end up looking like tangent. So if that ever happens, you're kind of just, reflecting it, turning it into the other one. Negative tangent would look like cotangent, negative cotangent would look like tangent. All right, so the directions here are easier, a lot easier to do tangent and cotangent than it was to do secant and cosecant. All you want to do is draw in your asymptotes. So for tangent, your first kind of period is between negative 90 degrees and 90 degrees. I can flip back to show you that one again. So your asymptotes, we're at negative 90, 90. So your first graph happens between those two. And then for cotangent, between 0 and 180 is where your asymptotes are. And then you kind of just sketch in your curves. So we'll do a couple examples and then we will finally be done with this. And actually one quick thing here that's kind of helpful is your 0 degree, just kind of your benchmark there. At 0 degrees, tangent has a graph. So your regular tangent then would kind of have a point there. Or kind of part of its graph is going on at 0 degrees. For cotangent, cotangent is going to have an asymptote. So those are kind of nice little benchmarks to work with. All right, so 2 tangent 3x. So amplitude, again, don't like totally think about it as amplitude. It's not really an amplitude, but it does have a vertical stretch of 2. The period, that's where, remember, we have to be very careful here. We don't do 360 divided by 3. We do 180 divided by our B value, which ends up being 60 degrees. So we're going to have a new graph, a new curve every 60 degrees. Phase shift, there is none. Vertical shift, there is none in this case. All right. So kind of remember our benchmarks here. So we want to start, well, before we even get to that point, I guess, we are starting this guy at 0 degrees. We can maybe go into negative land a little bit, but one complete cycle is going to take us 60 degrees. So I'm going to keep going a little more. I'm going to do 60 and then I'm going to do 120 as well. We'll kind of put some stuff in between there. We'll do 30 and we'll do 90 just to get a little bit better of a look. And then maybe we'll go back to maybe negative 30 degrees there. Okay, so what we're going to do here is we are going to remember that tangent starts at 0, 0, and it has its asymptotes 60 degrees apart. So our period is 60. So this is where we have to use our brains a little bit. So this is kind of the center of our tangent graph. The entire thing needs to happen within 60 degrees. So our asymptotes are actually going to be at negative 30 and 30, which is a whole cycle is 60 degrees. So that's a little tricky, but you'll get used to that as you do a few. There's going to be another one at 90 degrees because that would give us another 60 degrees, okay? Now, I would just kind of draw in your tangent curve like that, and then like that. And then we have a stretch here, and it's going to be really hard to tell exactly where your points are there, but I would just kind of put a 2 there and a 2 down there, just to kind of tell everybody that, yep, you know that this thing is stretched out a little thinner than it normally would be. So kind of have those guys there. All right, so I'm just going to hop over on Desmos really quick and just kind of make sure that we have our heads wrapped around this. So I'm just going to get rid of the cotangent, and then we have 2 tangent of 3x. Yeah, so you can see compared to the regular tangent, it's kind of stretched out vertically, and then it all happens in a shorter period. So I'll get rid of this again just for a second. Kind of zoom in a little bit and make sure that kind of looks like what we have. So we're going through 0, 0. We're going through 60, 0. We're going through negative 60, 0. And if we go back to ours, we have 0, 0 and 60, 0. So yeah, looking pretty good there. All right, and then just one more example. This is a cotangent example. So we just kind of want to fill our stuff in here. Our amplitude, there really is none, but we do have a vertical shift, or a vertical stretch, I should say. Vertical stretch of 2. Our period this time, we're gonna pretend we're working in radians here. It doesn't really say that, but we are. So remember, a regular period is pi, so we want to do pi divided by a third. Dividing by a third is the same as multiplying by 3, so 3 pi this time. There is no phase shift, and then the vertical shift is 2. Reason there's no phase shift is there's nothing here. So if we could set that equal to 0. We could do 1/3 x equals 0, but we're just going to end up with 0 anyway. All right. So what we kind of need to remember here where our asymptotes are. So remembering that for cotangent, you have asymptotes at 0. So I'm going to do, okay, there's 0, and then our period is 3 pi, and we only need to do 1 period, so let's just go with it. And then we can define the halfway point there. So basically, what's the difference, or what's halfway between 0 and 3 pi? Well, we can just do 3 pi over 2. Half of 3 pi would do it. And then in this case, we're shifted up 2 units. That's the big thing here. So instead of kind of starting right here where you would normally, because remember, for cotangent, your asymptotes are at 0 and at the end of your cycle. Typically, we would start there on the x-axis, but we have a vertical shift, so we're going to slide it up to here. And then I'm going to grab purple, and then we just need to remember that cotangent kind of goes that way. Like so. And these ones they're not going to look super perfect, but doesn't look too bad. And that's it. That's it for that one. So actually the tangent and cotangent ones can be a little bit easier for you. There's less steps. It's just kind of getting in the habit of the different period, and then just kind of dealing with the asymptotes versus the starting point and that sort of thing. So hopefully that helps. Sorry for the super long video. You can get going with the Graphing B worksheet at this point.